Did notice, though, is the name of the conference keeps changing. We used to have an MPLS World Congress. In fact, it was the MPLS Forum, but then there was a conflict with someone else, so it was the MPLS World Congress. Then it became the MPLS and Ethernet World Congress. And somewhere in there it said the MPLS and Ethernet World Congress thrown in with IPv6. Then it was the MPLS and SDN and Ethernet World Congress. Now it's the MPLS and SDN and Ethernet and NFV and IPv6, and I don't know what else there'll be. So I have a message here for you. I'm a geek. You guys know that. I have a geek talk with geek slides. There are very few pictures in here. Even my picture is like, But I want to give you two messages today. The first message is, it's lovely to go off and try new things. We have to do that. But we also have to do that because there's some practical value to those new things, not because it's a fashion statement. And the second thing is, we have to remember what works, and if it doesn't work, change it or fix what we have that works. So the specific talk I'm going to give you is about what do we do in the data center? What do we do as a fabric in the data center? And I've seen lots of talks where they talk about an IP cloth network or an IP fabric or so on in a data center. And so I'm going to talk to you about, can we do something different? In fact, what's different is we go back to basics, and we go back to using MPLS. And there's a lot of geek stuff about why and why not and how. But at the back of the mind, I would like you to keep the thought that we've wandered away from MPLS, which is good, and that's what helps the conference organizers to fill this conference room, which is great. It also, from our point of view as engineers, as technologists, we have to try new things. But sometimes we also have to come back and say, where do we start and how do we build on that? So the talk is about a native MPLS fabric for data centers. And this works in some way. OK. All right. So I'm going to start with the problem statement about the data centers. Everyone's talking about overlays. Overlays in the data center. Overlays have this wonderful property. If I do overlays right, then my equipment gets much simpler. I don't have to worry about state and so on. The reality is we've been doing overlays in networks for quite a long time. And we tend to either forget that or say, oh, that's in the network. In the data center is different. Well, the data center has servers, has storage, and a network. And so can we use techniques from the external network, from the WAN, from the metro, in the data center? And the answer says, yeah. So let's talk about why and why not put MPLS as one of the technologies in the data center. And to do that, we have to create an MPLS underlay network. And we have to make sure it extends all the way to the server, because at this point, the server is the endpoint of that network. So a server is not a pure server. It's mostly a server, but it has a network component. It has a NIC card. It has connectivity to the rest of the data center. So the goal here is to say, what are the characteristics of the network inside the data center? Do we build overlays? And I think the answer is yes. And how do we build those overlays? All right. There's a parallel question about how can I use MPLS in the access? And we've talked about this many times. We've talked about seamless MPLS and so on. And there the goal is, how do I take MPLS to some relatively, I mean, they're networking devices, but they're not sophisticated networking devices. So the DSLAM, the OLT, the cell-side gateway, how do I bring MPLS there? And one answer is, no, MPLS doesn't belong there. But a common answer is, yes, MPLS does belong there. Let's try to use technologies like LDP, downstream on demand. It's a simple technology. It gives you just enough information to be able to run MPLS to the access node. Well, there haven't been many implementations of LDP downstream on demand on DSLAMs or OLTs. So one question we can ask there is, was that the wrong choice? Maybe we should go back to VLANs or something else, PBBTE. But the other one is that we try to make this work. And here's the thing that, I mean, going back to this Uber theme, is MPLS failing us? And do we actually have to go after new things? Or are we not doing the right things with MPLS? So the question here is, let's have a different approach. Is it, let's take a new technology and try to make it work here, or take a new approach to the existing technology? So I'm going to use MPLS. I like the data plane. I like the associated control planes. But this last hop from the last sort of MPLS fully capable device to a device that needs to talk MPLS, get connected, but may not have the full power of the rest of the network. How do I bridge the gap? I've said this, but I'll go into it in a little more detail. Overlays are not new. Go back to ATM. We had VCs, VCIs, and VPIs. So essentially what we did there is to say, I can put 64,000 customers, one on each one on a different virtual circuit. I have a VCID for them, but I can bundle them into a VPI. So I'll have a virtual path, and I can aggregate many, many end customers into a virtual path. The basic idea was the processing, well, first, the state that you do is pushed to the edge. In the core, you don't do a fine-grained state. So the state in the core is reduced. The processing on the edge is on a per customer basis. The processing on the core is aggregated processing. We took the same idea for MPLS, which in my facetious moods, which I do have, I call MPLS a four-letter name for ATM. Essentially, you take PEs, provider edge devices, and you put lots and lots of state on them. You put state related to VPNs, you put state related to VPLS, you put state related to the addresses contained therein. And so you have tens of thousands of VPNs and tens of millions of edge state. You put them into an LSP, and you push that into the core, and you have much less state. So you're already doing overlays. You're already seeing the value of state compression or having to deal with much less state in the core of the network. So we've done overlays. We've done overlays and underlays. We've done this for a while. We see the benefits of it in terms of having detailed state on the edge and much more aggregated state in the core. What about the actual data plane? Can we use this data plane everywhere? Well, in the core, everyone uses MPLS. Now in the metros, people are beginning to use MPLS much more than they used to. In the data center, can we use MPLS? Well, the reality is commodity chips have implemented MPLS way, way back. I mean, a decade ago. In the 2004, 2005 timeframe, we had quite a few chips that say, we can do MPLS. Maybe we don't do all the fancy features, but label comes in, I can push a label, pop a label, swap a label, and send it to the next hop. And that's the basic thing you need for MPLS. Roll forward 10 years, and people have come up with new encapsulations, fairly complex ones. And the size of the encapsulation is a measure of how complex it is, because that means that in all these bits, you've got to look for the right bits to do what you need to do. So whether you need to do forwarding, whether you need to do customer identification or tenant identification, whether you need to do load balancing, the size of the encap tells you some of that. But they have gone ahead and implemented this in the commodity chips. So one of these encapsulations, VXLAN, has been implemented, and I'm told that NVGRE is either out or imminently out. But as we speak, there's yet another encapsulation, that being Genève, which is trying to combine VXLAN and NVGRE. And then there's an older one called STT. So there's a number of them. There's MPLS over GRE, MPLS over UDP. the number of encapsulations that you have is huge. So is this a good thing? Well, in the spirit of playing, in the spirit of experimenting, in the spirit of not being locked down to one thing, in the spirit of innovation, these are great things. But they've forgotten another really important part. With the overlay and underlay come control planes. If you look at MPLS, I have a very sophisticated, scalable, robust control plane. It's been deployed, it's interoperable, and it's been in the networks for a long time. And people come and complain to us about it. That's what they do. But they don't complain to us about so much of it. They'll complain about a couple of features that they want. The bulk of it works. It scales. It does a lot of great things. And then they want more. We have hierarchy. And this hierarchy is really important because it lets you separate the services from the core. So the data plane, the value of the data plane that you just saw is reflected in the control plane. So I told you that on the edge, you have tens of millions of things that you want to deal with. And the core, you have tens, or well, hundreds or thousands of things you want to deal with. The control planes reflect that. I use BGP or targeted LDP on the edge. I use LDP or RSVP or LDP over RSVP in the core. So I have a very good data plane. I have a very good control plane to go with it. The new overlay encapsulations basically say you're on your own. Especially the latest one, Genève, which is trying to mix everything together, explicitly says we're trying to keep the data plane independent from a control plane, which is not a bad idea. But give me a control plane. It's nice that I can mix and match control planes, but give me a control plane. So there has been some things in this direction that we'll use BGP, which provisions edge services like internet access and VPNs and eVPNs and VPLS. We'll use that with VXLAN, with NVGRE, and with anything else you bring. And I'm happy that that's happening. But at the end, it's an afterthought, and we're trying to at least get the overlay control plane. We still need to figure out what the underlay control plane is. Why IP? Why do we go down this path? Whether it's MPLS over GRE or MPLS over UDP or NVGRE or VXLAN or Genève or STT, why are we going down this path? The theory is IP is simple. It's plug and play. It's well understood. I can hire people who can debug the network for me. All forwarding chips do IP, and not just all. Forwarding chips, forwarding software as well. The network interfaces cards can do IP acceleration through offload. So this is great. And IP is ubiquitous, so this is the right answer. All true, but I'll give you some reasons why maybe not IP. IP encapsulations are pretty heavyweight. I mentioned slightly before that the encapsulations tend to be pretty big. Yes, it's a few more bytes, and it's not about bytes. It's not about whether it's 20 bytes or 4 bytes. What it's really about is if you put in all those bytes, I have to put in, or somebody has to put in, a lot of gates that will process those bytes and say, what can I do with this? So VXLAN and NVGRE are relatively new. Yes, we've tried to put them into forwarding, but now we have to also do that in software. So the Contrail guys are going ahead and adding VXLAN-based encapsulation and NVGRE-based encapsulation to their code, their equivalent of the vSwitch, to be able to process all this. It can be done. Yeah, absolutely. Broadcom is doing the same, and they've done it for their chips. That's harder to do. They've done it. It's not whether it can be done. It's more work for them to do. And in the end, if I have a chip or a forwarding piece of software that says, I can do MPLS, I can do MPLS over GRE, I can do MPLS over UDP, I can do VXLAN, I can do NVGRE, I can do STT, yes, this is all great. Are we helping the industry move forward? The other thing is, each one brings its own complexity, and then trying to interoperate between them to say, OK, in this part of the network, I'm using VXLAN. In this part, I'm using STT. Someone has to do all the mapping from one to the other. I have all these further features. Just NCAP, DCAP is not enough. I need to do load balancing well. I need to have an answer for fast readout. So if a link fails, how am I going to move my traffic to the right place? How do I do all these things and then do them n times over in all these different encapsulations? The second point is IP is ubiquitous. Well, MPLS is not ubiquitous, but it's pretty widespread. Every core network is running MPLS. A lot of metro networks and access networks are now running MPLS. The last standout is the data center, except if you go and look in some of the content providers, their data centers are also running MPLS. So from the point of view of IP is ubiquitous, I think you can say MPLS is also fairly ubiquitous. So at least you can't rule out MPLS because of that. The other part is MPLS is proven to scale and to be robust. So, and it, of course, supports multi-tenancy, which is a fancy way of saying VPNs. So one of the things we have to do is take all the terminology that we had in MPLS and bring it to this new language. So instead of saying overlay and, instead of saying PE and P, you have to say overlay and underlay. Instead of saying VPN, you say multi-tenancy. Yeah, it's very important. So the fact is, we can use MPLS. We have the chips to do it. We have a control plane to do it. We have the data plane to do it. So what's wrong? So the question of why not MPLS is complex, hard to provision, hard to understand, hard to troubleshoot. And the other thing is, we don't need MPLS in the data center. We have a very systematic, well-structured network in the data center. The wide area is messy. You put fiber where you can. The distances are different. There are differences in latency, differences in a bunch of things. So I need a fancy IGP, and then I need traffic engineering and everything. But in the data center, I don't need any of that. Well, the reality is, networking is complex. So even this so-called simple IP networking, when stuff breaks, you don't know where it breaks. And it's not that IP is bad or MPLS is good or Ethernet is bad or someone else is good. We don't always come up with the right operational tools. And it's a failing of the industry. And so, for example, someone mentioned this earlier today, MPLS had been around for about 4 or 5 years in production before we came up with MPLS ping. And that's just a starting point. And later we added the performance measurement. So first, I can set up LSPs, but I don't know if they're working. Second, I can tell you whether they're working or not, but it's a binary yes, no. And then more recently, I can tell you they're working well or they're working not so well. So it's not yes, no, it's all the grays in between. So we need to focus on this. And we need to say, how can we do the right thing here and use the right protocol and fill in the gaps that we're missing, rather than saying, oh, we'll throw out everything and start again. Because it looks really nice to start again. It's a lot of work to bring MPLS to the place we brought it. To the second point, that MPLS features are not needed in the data center, MPLS features are actually really needed in the data center. Sophisticated load balancing. People are saying, I need this load balancing to be really good because I've got lots of traffic going through my network. My servers are pumping out 10 gigs of traffic, and my infrastructure is 10 gig. And yes, I will move to 40 gig and 100 gig infrastructures, but meanwhile, this is what I have. And even if I move to 40 gig and 100 gig, especially at 40 gig, lots of 10 gigs going through this means I better be able to load balance my stuff. So sophisticated load balancing. The second thing is traffic engineering. Why would I want traffic engineering in the data center? If I can identify, so we talk about elephant and mice, which is basically very fat flows and thin flows, small flows. And if I treat them equally, I'm going to have a mess. I'm going to have lots of congestions and packets dropped. So if I can identify and traffic engineer the elephant flows away from the rest of the network, I can do a much better job. So I would never need traffic engineering to, wow, this would really help me. And then fast readout. I mean, there are lots of critical apps. You want to make sure that they work well, and if something in the network fails, they see as little interruption as possible. In fact, to the extent that you might even do live stuff. So you have two parallel paths, both carrying live traffic. So we need the features. MPLS works in the control plane. MPLS works in the data plane. You know, what's wrong with this? The bigger question is, what do we do about overlays? Having a proliferation of overlays is not helping the industry. We just keep doing this, and you know, you think you're done, and the next one comes, and you think you're done, and the next one comes. We can do this, and we should. We should, at least as a sideline, do this and make sure we're not missing something. But at the same time, we have a protocol that works. And so rather than trying to invent new protocols all the time, we can also say, what is the gap of the current protocol? What's the step that would let me go from where I am to where I need to be? And if it's a small step, maybe that's the right thing to do. If it's a big step, then maybe an alternate is more interesting. But at the end, whatever your choice is, yes, I'm an MPLS guy. I will advocate MPLS. But if the industry converges on one way of doing this, at least for a particular domain, here's the one way of doing it, and we do it well, and we consider all aspects, so the data plane, the features, the control plane, and their features, and how they work together, we've done a good job. Right now, we're just spread really thin. So what's the gap in MPLS? Well, I said the MPLS control plane is very sophisticated, very scalable, all these beautiful features. But I think that in this case, it is too sophisticated. If you take a biggish data center, I've got thousands of top-of-rack switches. Each top-of-rack switch hosts, let's say, 50 hosts. And by the way, I'm going to use the word host rather than server, because I'm going to use a protocol where the server runs as a client, and so it's confusing. So a host is a Linux server. So I've got thousands of nodes in the network of the data center. I've got tens of thousands or hundreds of thousands of hosts. Each of those hosts are hosting tens or hundreds of VMs. So at the end, I've got tens of millions, if not hundreds of millions, of virtual machines in my data center. How do I scale this? Well, let me start with the underlay. If I said use MPLS, I would have to use LDP or RSVP and then build on top of that. Well, to take RSVP to the host, I would have to have a multi-layer IGP. So I either have multi-level ISIS or multi-layer OSPF. That's a complete non-starter. This has to be completely plug and play. So how do I just rack 20 new servers and not worry about it, and not worry whether they're in the right area number or they have the right ISIS system ID? I have to do this in a way that's completely plug and play. Well, what do we use today? We use ARP. Can we use ARP for MPLS? So before I get there, and I don't know how much time I have. 5. OK. Let me start with proxy ARP. How does proxy ARP work? I've made Dave so tired he had to sit down. So proxy ARP, essentially, I have host 1 saying I want to talk to host 2. I know his IP address is IP2. So he's going to send out a request saying, hey, I want to get to IP2. Give me a MAC address to reach him. And if the Tor has connectivity to that IP address, he's going to essentially say, here's a MAC. Use this MAC. I'll make sure the packet gets there. So this is not ARP per se. This is a proxy ARP. So if I want to label ARP, the first step is to make sure I have connectivity from the Tor to all the hosts. So I'm just going to skip through this quickly. Essentially, I'm going to have an LDP network. And to keep it really, really simple, I'll have the Tor in the end, Tor T2, leak all the addresses of the host belonging to him into LDP. So Tor T1 says, I have a label, L2, that will reach IP2. So now, when we come back to our host, H1, H1 says, give me a hardware address, in this case, MPLS over Ethernet address, that will get me to IP2. And so we have a new hardware type. So I don't want just a MAC, I want a label. So T1 says, I can reach this guy. My LDP setup let me reach this guy. So all I have to do is allocate a label, stick it in my fib. I'll allocate label L1 for this. And what I have to do is swap L1 with L2, and then the packet will reach IP2. And so he sends it back in the ARP reply saying, here you are. Use my MAC and label L1. And you have to prepend it with the MAC because labels are not global. So now you have a protocol that's completely plug and play, a protocol that scales reasonably well because we're doing proxy ARP, not end-to-end ARP. So you have 50 servers talking to one top-of-rack switch. That's a very contained, scalable problem. And now H1 is connected into the MPLS network. Now, it's connected specifically to H2, and if he had a different host he wants to get to, he'll do another ARP for that. So he might end up saying, I need to talk to 50 hosts at this point, so I'll get 50 ARP requests sent out. I'll get 50 replies, and I'll have an LFIB that has 50 entries in it. And then as things change, the VM moves from here to here. I have to get new addresses and old ones time out. All that happens. It's pretty much ARP operation, but from the host point of view, he has only the labels he needs, and he got them in a very simple plug-and-play way. So if he sends a packet with L1, the Tor will swap it with L2, and it'll go through the network. It'll get to Tor2 with label L3. Tor2 says, I'm going to pop it and send it to H2. So functionally, this is very similar to LDP downstream on demand. But from a code point of view and from a familiarity point of view, this is so much easier. So the goal is, can we get this code out there to everyone, to access vendors, to the Linux distribution, so that you put up your server and boom, it's already there. So the points to note: ARP is ubiquitous. Every device has ARP. We're not quite at the point where I have an iOS app that does labeled ARP, but please feel free to do that in your spare time. There's an IETF draft that describes this, so it's an open standard. There's prototype code that does this, and eventually this will be open source code on the client that does labeled ARP. So the goal is to make this really, really available. There are a couple of use cases. I'll only go over one of them. But essentially, this is not an MPLS use case. This is a use case where I have a content server. If this thing works. Oh, never mind. So I have a content server. Wrap up. OK. So I have a content server, the two peering points, ISP1 and ISP2. And I want to send traffic to the right guy. IP traffic comes to the content server saying, give me this video, and I want to stream the video back, but over the right peering point. You can do this in many ways. People have used MPLS over UDP, over GRE, and people have used basic MPLS. So this is a use case where MPLS in the data center really makes sense. Another use case is MPLS just for VRFs. So I want to come back to the basic premise here. We have too many overlay mechanisms. We have too many data planes. We have too many ways of doing things. They're all very similar and doing very similar things, but they're all very different when it comes to implementation. That's not helping. I'd like us to come back and focus on one to make sure that we have one that does all the features that we need. I think it's MPLS. It might be something else. Make a proposal. But if it is MPLS, go to our booth. You can see a demo of how this works. And then if the industry can all choose one and focus on that, I think we'll all be in a better place. Thank you.
Thank you, Kireeti. Question. OK, I'll take Michael first. Mike?
Just shout.